Back in the early days, city buses looked nothing like the ones you see on the road today. Their engines sat right at the front, directly behind the driver, much like a standard truck. That setup worked well for decades, but sometime in the 1950s, engineers began making a quiet shift. Instead of keeping the engine up front, they started placing it at the rear of the bus. No big announcement, no dramatic redesign reveal, just a gradual change that spread through transit systems nationwide until it became the standard design we still use today. Before we get into the engine placement, it helps to understand what makes a transit bus different from your average truck or van. A transit bus is a heavy-duty passenger vehicle designed to follow the same route over and over, make frequent stops every few blocks, carry both seated and standing passengers, and do it all reliably for 12 to 15 years. That's a completely different job compared to hauling freight across long distances. The earliest motor buses, dating back to the early 1900s, were essentially modified motorized wagons. Their engines were mounted at the front, the driver sat above or just behind it, and passengers boarded through a rear door. This setup, known as the front engine, front radiator design, was borrowed directly from trucks, which makes perfect sense since the first bus builders were actually truck manufacturers. The biggest problem with a front engine bus is simple. The engine takes up a huge amount of space. When it's placed beside or directly behind the driver, it creates a large mechanical hump that pushes up into the passenger cabin, right where people need room to walk, stand, and move around. On older city buses, this created a stepped floor with raised sections near the front. Passengers had to climb up and over it just to move through the bus. For elderly riders, that was already difficult. For passengers with mobility challenges, it made access even harder. And in an emergency, those raised sections could slow people down when every second mattered. There was also another issue: weight distribution. A heavy engine sitting up front, combined with a full load of passengers packed toward the rear, put uneven stress on the front axle. In busy, transit-heavy cities like New York, Chicago, and Los Angeles, that extra strain meant faster wear and tear, not just on the buses themselves, but also on the roads they traveled every day. Clearly, something had to change. Moving the engine to the rear solved several of these problems at once, but it also introduced a few new engineering challenges, and the way engineers solved those trade-offs is where things get really interesting. In a rear-engine bus, the diesel engine is mounted horizontally inside a compartment at the very back of the vehicle. It's laid on its side rather than standing upright, which is very different from how most engines are installed. That design required an entirely reworked drivetrain. Think of it like sliding a filing cabinet under a bed instead of standing it in the corner of a room. You still get the same storage space, you just have to access it in a completely different way. With the engine no longer sitting under the passenger floor, the entire cabin can sit lower and stay flat from front to back. That's why modern low-floor buses, commonly used on city routes across the US, sit only about 12 to 14 inches, 30 to 35 centimeters, off the ground at the front entrance. That low height allows a simple ramp to deploy for wheelchair access, eliminating the need for bulky lift systems. Even the cooling system had to be redesigned. Since the engine is now at the rear, the radiators are usually mounted either on the roof or along the back of the vehicle, allowing airflow to keep everything running at the right temperature. Air is pulled in through specially designed vents, circulated through the system, and pushed back out, all without taking up valuable passenger space inside the cabin. It might sound like a small design detail, but it's actually one of the more complex engineering challenges of the entire rear engine setup. The rear engine layout excels in three major ways, and each advantage builds on the others. First, better weight distribution. With the engine positioned at the rear and passengers spread more evenly throughout the cabin, the load is balanced far better between the front and rear axles. The Federal Highway Administration, FHA, sets strict axle weight limits, around 20,000 pounds, 9,000 kilograms, for a single axle. A more balanced design allows buses to carry more passengers while staying within those legal limits. Second, easier maintenance and servicing. On most modern transit buses, the rear engine compartment opens fully from the back, almost like a giant hatchback. That gives mechanics direct access to the entire powertrain, allowing them to remove or service major components without tearing apart the passenger interior. It saves time, reduces labor, and keeps buses back on the road faster. On older front-engine buses, doing that same maintenance often meant partially removing the driver's cab just to reach major components. Third, and this is the advantage most people never think about, is safety. With the engine mounted at the rear, the driver sits farther away from heavy mechanical components. In a front-end collision, that creates more crumple space between the driver and the impact zone. And at 40 miles per hour, that extra distance can make a serious difference. Rear engine layouts aren't limited to city transit buses either. You'll find them in other vehicles too, often for completely different reasons. Take school buses, for example. They're actually a great comparison. Most American school buses still use a front-engine design because their operating needs are completely different. They usually travel at lower speeds, make fewer stops per mile, and don't need the low, flat floor that city transit buses depend on for quick boarding and accessibility. When the job changes, the engineering trade-offs change with it. Then there are motor coaches, the long-distance buses people use for travel between cities. These switched to rear-engine designs decades ago. Why? Because moving the engine to the back frees up a large storage compartment underneath the passenger cabin, creating valuable luggage space, something that's essential for that kind of service. And then there's the Ferrari 308. Yes, a sports car. It uses the same basic concept, placing the engine at the rear for improved weight balance, but for an entirely different purpose: performance and handling. Same engineering solution, completely different problem. And honestly, that's one of the coolest things about engineering. A smart idea in one field often finds its way into another, solving challenges nobody originally designed it for. The rear engine layout isn't perfect, and it does come with its own set of challenges. One of the biggest is heat management. When the engine is packed into a tight rear compartment, getting rid of heat becomes more difficult. In hot regions or in heavy stop-and-go city traffic during summer, rear-mounted engines can run hotter than front-mounted ones. That's why transit agencies in places like Phoenix and Miami have to put extra focus on cooling systems compared to cities like Minneapolis, where temperatures are much lower and conditions are less demanding. But the bigger change happening right now isn't about front or rear engines at all. It's electrification. Electric transit buses, such as those developed by companies like Proterra in Burlingame, California, and BYD, which operates a major facility in Lancaster, California, take the entire engine layout question in a completely different direction. With electric drivetrains, the motor can be placed directly at or near the axle, which largely removes the traditional constraints of engine placement. Instead of worrying about engine space, engineers now focus on where to position the battery pack, since that becomes the main factor in weight distribution and design. This shift is still ongoing, but by 2024, electric buses accounted for roughly 10% of all new transit bus orders in the United States. So the next time you step onto a city bus, that flat, open floor isn't just a design choice. It's the result of decades of engineering evolution, solving real problems with real trade-offs, and shaping how public transit works today. And that brings it full circle. What part surprised you the most? Let it know in the comments. We read them all.